is problems 1 through 20 of the AMC 10A. So first, this is problem 1 of the AMC 10A and also problem 1 of the AMC 12A. So what is the value of 3 plus 1 over 3 plus 1 over 3 plus 1 over 3? So this is a continued fraction, right? So we have multiple layers of a fraction. And whenever we have multiple layers like this, we always want to evaluate from the inside first. So first we evaluate this, then we'll flip it because 1 over is just a reciprocal, right? Then we add 3 more, then we put 1 over and then add 3 more. So 3 plus 1 over 3, 10 over 3, 1 over 10 over 3 gives us 3 over 10. Then we add on 3, which is 30 over 10. If we add that on, we get 33 over 10. 1 over 33 over 10 is 10 over 33. And then we add on 3, which is 99 over 33 more. And then if we combine these two, we end up with 109 over 33, which is choice D. All right. Now this is problem 2 of the AMC 10A. Mike cycled 15 laps in 57 minutes. Assuming he cycled at a constant speed throughout, approximately how many laps did he complete in the first 27 minutes? Well, first off, we can immediately tell, well, 27 is about half of 57, so we should have about half of 15. Half of 15 is around 7.5. So we can already tell that approximately it's going to be closest to 7, but we should probably do the test anyway, because we might as well do the calculation anyway, because the answer might happen to be 9, right? So let's do 15 times 27 over 57. That is 15 times 9 over 19, which is 135 over 19. And actually 19 times 7 is 133, which means that this is 7 and 2 19ths, which is of course closest to 7. So that's our answer. All right. Now this is AMC 10A number 3 and also 12A number 2. The sum of 3 numbers is 96. The first number is 6 times the third number, and the third number is 40 less than the second number. What is the absolute value of the difference between the first and second numbers? Okay, well, because the first number's value relies on the third number value and the third number's value relies on the second number value, we should just set the second number's value first. Let's call it the variable x. Well, the third number is 40 less than it, x minus 40. And the first number is 6 times the third number, which is x minus 40. And basically, the way we have all of these things being related is that the fact that their sum is 96. So if we expand this, like this is 6x minus 240, then we end up getting 8x minus 280 equals 96. So we can divide by 8 to get this. So x is equal to 47. So that gives us this value as 47, and also gives us this as 7, therefore, and therefore gives us this as 42. And we can check, yes, this meets all the stipulations of the problem, right? 47 plus 7, 54 plus 42, that gives us 96. So we know these are the right numbers, and the absolute value of the difference between the first and second numbers is just 5. Okay, now AMC 10A number 4. In some countries, automobile fuel efficiency is measured in liters per 100 kilometers, while other countries use miles per gallon. Suppose that 1 kilometer equals m miles and 1 gallon equals L liters. Which of the following gives the fuel efficiency in liters per 100 kilometers for a car that gets X miles per gallon? Okay. So what is the fuel efficiency in liters per 100 kilometers? Well, first off, right now, we're given that it's X miles per gallon. And miles goes with kilometers and gallon goes with liters. So it's actually flipped the wrong way around. So we got to flip that real quick. So if it's X miles per gallon, then that would mean that the rate is 1 over X gallons per mile. So now we can convert that to the rate we need. Well, the thing is 1 gallon equals L liters. So basically what this rate is really saying is that there are, for every 1 over X gallons, for every 1 over X gallons, we are able to go 1 mile, right? Which means that, well, if it's 1 over X gallons, we know that 1 gallon equals L liters. That means that to convert from gallons to liters, we need to multiply by L. So we multiply by L, so 1 over X times L. So 1 over X times L times G, right? So basically, this ratio becomes 1 over X times L to give us the liters per miles, right? And the thing is, we need to do the same thing for the miles. Well, 1 kilometer equals m miles, which means 1 mile is 1 over m kilometers. So basically down here, we need to multiply by 1 over m, but the thing is, it's in the denominator, right? So it's 1 over m. So this would actually cancel out and just give us this number being multiplied by m to give us lm over x, right? So let me just re-summarize that. To convert from miles to kilometers, we divide by m, but the thing is, m is in the denominator, which means m is being divided itself. So we're dividing twice, which gives us the reciprocal of the reciprocal, which gives us multiplication, right? So this m is actually being multiplied. So it's lm over x liters per kilometers now. I forgot to write this in as kilometers, my bad, but this is, oh, no, never mind, wait. This is liters per that, and now we get that this is liters per kilometers. So yeah, basically this is a very confusing rates problem, but we get lm over x, and now the final part of the problem is whether or not the 100 goes on the top or the bottom of the fraction, which is very, very trolly, because it's very easy to think, well, they added a 100 to the denominator, right? It's liters over 100 kilometers. So therefore, this is being divided by 100. But that's not true. Because they multiplied this denominator by 100, what that's really doing is that requires us to multiply the numerator by 100 to have things cancel, right? So we would actually get 100 lm over x, right? And the reason for this is simple, right? If the fuel efficiency is so many liters per a kilometer, then if we're measuring liters per 100 kilometers, that means each of those 1 kilometers gives us that amount of liters. So 100 of those kilometers would give us 100 times the amount of liters. Okay, so that is very confusing, but the answer is 100 lm over x. But what we can actually do to check our work here, right, because it's very easy to mess up on this problem, is we can try plugging in arbitrary values, right? Like, for example, what if we say m equals 2 and L equals 3 and X is 4, for example, right? And that could make it a lot easier to visualize how the problem works, right? So potentially plugging in numbers instead to check the answer here could help, right? But in this case, we're not going to check it here because this is the correct answer. Yeah, so now this is AMC 10A number 5. So we have square ABCD, and it has side length 1. And now it's saying points P, Q, R, and S each lie on the side of ABCD so that APQCRS is an equilateral convex hexagon with side length S. What is S? Okay, well, in order to make an equilateral convex hexagon, well, of course, the hexagon would probably have to have some shape like this. Like we can try drawing it, and it would probably have to have some shape like this. And of course, that would mean P is here, Q is here, R is here, and S is here, right? So we can draw it more precisely now. And we have to try to draw it so that it's equilateral. Probably like that. That's pretty much equilateral. Yeah, it's not. There we go. It's like this. That's the hexagon. And it's equilateral, which means all of these side lengths are S. And now it's just asking us to find the side length S. Well, this isn't too difficult because this is just an isosceles triangle, right? Because this is S, which means this is 1 minus S, and this is 1 minus S. So this is an isosceles right triangle, which implies that S over 1 minus S is in the ratio of root 2. And that's it. Now we can solve the problem from here because S is equal to root 2 minus S times the square root of 2, which means that S times 1 plus root 2 is equal to root 2, which means S is equal to root 2 over root 2 plus 1. And now to conjugate the denominator, we can multiply by root 2 minus 1. And that'll give us, well, this is just 2 minus 1 down here, which is 1. So the denominator goes away, and we're just left with 2 minus root 2. So that's our answer. Okay, now this is AMC 10A number 6. Which expression is equal to the absolute value of a minus 2 minus the square root of a minus 1 squared for a less than 0? Okay, so there's one thing that needs to be clarified here, which is what is the square root of a minus 1 squared? Well, it might seem like the square root of x squared is just x, right? But the thing is, that's actually not true for the case of this problem. This is not true. And the reason for this is, for example, if we plug in any positive number, right, then yeah, square root of 3 squared, that's 3, right? Square root of 4 squared, that's 4, right? Maybe like square root of 2.7 squared, that would just be 2.7, right? Square root of x squared is x, but only if x is positive. If x is negative, then this happens, right? Square root of negative 2 squared, well, negative 2 squared, that's 4, and then square root of 4 is 2. So if you notice, plugging in a negative number will also make it positive, right? So now we can realize from this that the square root of x squared is actually equal to the absolute value of x. So we can replace that into the problem. And now we see that we can easily solve the problem from here because both absolute values, when we solve them, basically because a is less than 0, we're able to determine whether or not the thing inside the absolute value is positive or negative. And actually, in both cases, it'll end up negative because in this first one, well, a minus 1, we're taking a negative number, a is negative, and subtracting more stuff. So it's obviously going to be negative. So basically, this would become negated, right? It would become negated to turn it into a positive number. So we would get 1 minus a. So we'd be subtracting 1 minus a, right? But that, when we simplify it, just gives us 2a minus 3, the absolute value of 2a minus 3. But once again, a is less than 0, so 2a is less than 0, and 2a minus 3. If we're subtracting more from a negative number, it's going to be even more negative, right? So it's not going to go into the positives. This is going to be negative, so we're going to invert this and get 3 minus 2a, which is choice A. Okay, next up, this is AMC 10A, problem 7. The least common multiple of a positive integer n and 18 is 180, and the greatest common divisor of n and 45 is 15. What is the sum of the digits of n? Okay, so let's just refresh on what LCM and GCD are again. So LCM is the smallest number that is a multiple of both of these numbers. So 180 is the smallest number that such that it is a multiple of 18 and a multiple of n. And 15 is the GCD is the reverse. It's the largest number that is a factor of both numbers. So 15 is a factor of 45 and a factor of n. So what this tells us is that n has to be a multiple of 15, but 180 has to be a multiple of n. So 180 has to be a multiple of n, which also has to be a multiple of 15. And this immediately narrows the possibilities, right? Because if we write down the multiples of 15, right? Well, the thing is, 180 is just 15 times 12, right? So n only has options of 15, 15 times 2, 15 times 3, which is 45, 15 times 4, 15 times 6, and 15 times 12, which is 180, right? These are our only options because those are all the factors of 12 multiplied by 15. But there are several problems with these numbers. One of them being that 45, 90, and 180 are all not going to work because they're multiples of 3. And actually, no, I mean, they're multiples of 9 specifically. They're multiples of 9, which isn't going to work because that'll make the GCD of n and 45, 45, right? Because 45 divides both of them in these 3 cases, right? So basically the GCD of n and 45 would be 45 in these 3 cases. So none of these would work. And furthermore, we need to have n be a multiple of 4, right? N has to be a multiple of 4 because let's say n isn't a multiple of 4. Well, then 90 would work, right? Because 180, that's a multiple of 4, right? Like, for example, in the case of 15, well, 15 and 18, their LCM would just be 90, right? And it's the same case with 30. The LCM of 30 and 18 would just give us 90, right? So these 3 also don't work. So our only answer left is 60. And the sum of the digits is just 6 plus 0, which is 6. All right, this is AMC 10A problem 8 and 12A problem 6. The data set consists of 6 not distinct positive integers. So they're not distinct. They can be the same. And also we have to keep in mind that they're positive integers. That's very important. 1, 7, 5, 2, 5, and x. The average of the 6 numbers equals a value in the data set. So the average of the 6 numbers, let's just add up these numbers and put them over 6. This is our average, and this has to equal a value in the data set. And there's only 5 possibilities for this. Either it equals 1, it equals 2, it equals 5, it equals 7, or it equals x. These are our 5 possibilities. And if we simplify this further, this sum here is equal to 20. So 20 plus x over 6 has to be one of these 5 numbers. Okay, well, let's just multiply both sides of the equation by 6. Well, then this would become 6, this would become 12, this would become 30, this would become 42, and this would become 6x. Okay, well, in the case where these are constants, all we would do to solve for x is subtract 20. So in the case of 6, for example, x would just be 6 minus 20, which is negative 14. In the case of 12, it's negative 8. In the case of 30, it's 10. In the case of 42, it's 22. And then for the case of 6x, what we would do to solve the equation is subtract x to get 5x equals 20. And then from here, we get x equals 4. So these are all the possible values of x. Except summing all these numbers, right? If we did sum up all these numbers, it would give us 14, which isn't even on the answer choices. And the reason for that is, like I said before, positive. Positive is a very key word here because these two are negative. Negative is not positive. These are not solutions. So it is just these three. So we would just add up those three, 10 plus 22 plus 4, and that would give us 36. Okay, this is AMC 10A, problem 9, and AMC 12A, problem 7. A rectangle is partitioned into 5 regions, as shown, these 5 regions. Each region is to be painted a solid color, red, orange, yellow, blue, or green, so that regions that touch are painted different colors, and colors can be used more than once. How many different colorings are possible? Okay, so this is a very simple problem if you know what order you can color these in, because, well, we can choose any order to color them in. And of course, if we count the right way, we'll get the right answer, right? So we can think about the problem in a smart way. We can think about the problem in a smart way instead of trying to count all the possibilities. Like, think about it like this. Let's say we start by coloring this region. How many ways are there to color that region? Well, 5. Let's just say that I color it red, right? There's 5 ways to do that. Okay, well, let's move on to another region, right? Well, this region is touching red, and according to what the problem says, regions that touch are painted different colors. So this can't be red. It has to be orange, yellow, green, or blue. Okay, let's say I color it blue. Well, of course, there are 4 ways to do that. Okay, let's move on to this section that's touching both the red and the blue. How many ways are there to color it? Well, that's simple. There's 3 ways to color it. But the key thing here is the fact that no matter what first 2 colors I picked, the number of ways we could color this next region has to be 3. It has to be. There's no other way, right? Because those two colors that is touching are also touching each other. So they have to be 2 different colors. So there's only 3 colors left. Okay, let's say I color it yellow. Well, let's move on to this region. How many ways are there to color that region? Well, it is touching the yellow and the blue. It's not touching the red, so it can be colored red, which means that there are, once again, 3 possibilities. Okay, let's say I color it red again. Okay, well, now let's move on to this final region. How many ways are there to color it? Well, it's touching red and yellow. And like we already mentioned, there's no way for these two to have been the same color or something, right? They have to be 2 different colors. So we only have 3 colors left out of the 5. So let's say I color it orange. Well, we know that can be done in 3 ways. All right, and now we can just use the fact of counting the multiplicity rule, which basically states that if there are like A ways to do one thing and B ways to do another things, then to do the first thing followed by the second thing is the product of them. That's how many ways, right? Because there's A ways to do the first and B ways to do the second. If they're independent events of each other, which we have shown they're independent, right? Like this having 3 colors left is independent of what we did the previous steps. We'll always have a different color here, different color here. That's what it means for things to be independent. So this number 3 here is independent of how we chose the previous colors. So this independence is what shows that the number of ways to do A followed by B is the product. And this applies to more than just 2. In this case, we're going to use it with 5 numbers, right? So basically, there's 5 ways to color the first box, 4 ways to color the second box, 3 ways to color the third box, 3 ways to color the fourth box, and 3 ways to color the fifth box. So that would give us final answer of, well, this is 20, this is 27. Our final answer will be 540. Okay, This is problem 10 of the AMC 10A. Daniel finds a rectangular index card and measures its diagonal to be 8 centimeters. Daniel then cuts out equal squares of side 1 centimeter at two opposite corners of the index card and measures the distance between the two closest vertices of these squares to be 4√2 centimeters, as shown below. What is the area of the original index card? Okay. Well, there are two variables that we need to keep in mind here. One is the length of the index card, one is the width. Let's call them A and B. Let's call this, that'll be A. Let's call this B. Okay, well, what does this 8 mean then? Well, 8, that's the full diagonal, right? Well, by the Pythagorean theorem, that means that A squared plus B squared is equal to 8 squared, which is 64. Okay. Well, now the harder question, what exactly does this 4√2 mean? Well, if you think about it, because this is a rectangle and this is like little squares, right? Everything is right angles. And the good thing about right angles is we can shift things down. So basically, we can shift things across and preserve their length because of rectangles having opposite sides the same length. So for example, here, if we make this, if we draw this extension here, these are all right angles. This is a rectangle. So since this length we know to be 1, this is also 1. And this is 1, which means that this is just A minus 2. And we follow the exact same set of, we follow the exact same steps to get that this length here, right? This length, like this length here is B minus 2. And this, oops. And this length here is A minus 2, right? So disregarding those edges, right? So basically what that tells us is by the Pythagorean theorem, A minus 2 squared plus B minus 2 squared is equal to 4√2 squared, which is 32. Well, now we have enough information to solve the problem, right? Because we have two variables and two equations. We can solve for A and B. So let's do that. But we'll go about it in a way where we don't even solve for A and B. Let's just solve for the product AB. We don't need to solve for it. And what I mean by that is we're going to expand this. A squared minus 4A plus 4 plus B squared minus 4B plus 4 is equal to 32. And that means, well, this A squared and this plus B squared gives us a 64 in the equation, right? Because A squared plus B squared is equal to 64. And then minus 4A minus 4B is equal to 32 minus 4 minus 4, because we're subtracting both 4's, 24. And now that just gives us that 40 is equal to 4A plus 4B, which means that 10 is equal to A plus B. And now we can go back to this equation combined with this equation, because if we square this equation, we get A squared plus B squared plus 2AB is equal to 100. But A squared plus B squared is 64. So if we subtract the two equations, 2AB is just 36, and AB is equal to 18. And if you look back at what the problem's asking for, it's asking for the area of the original index card. That is the area before Daniel snaps those two squares out from it, right? The original index card, before he snaps out those two squares. That's the key of this word here, original. So it's not 16. We don't subtract 2. The answer is 18. Okay, this is AMC 10A problem 11. Ted mistakenly wrote 2 to the m times the square root of 1/4096. And he accidentally saw this m here and was like, oh, that must be the mth root of 1/4096. You know, it happens. You make a mistake like this. But we're looking at the situation where Ted gets lucky and these two are equal. So making this mistake doesn't change his answer. Basically, that's the whole point of this problem, right? So the question is, what two real numbers m makes Ted lucky where he doesn't accidentally get the wrong answer, basically. So, well, we can simplify what we can. Let's just set these equal to each other and write in this product, right? So this is 2 to the m times the square root of 1 over 4096. And one thing to keep in mind is that if you just multiply 4096 by itself, like if you just divide 2 from it a lot of times, you'll figure out that its prime factorization is just 2 to the 12. So that's very helpful because that implies that this is 1 over 2 to the 6. So this is 2 to the m times 1 over 2 to the 6. But it's, yeah, because of the square root, it makes it 1 over 2 to the 6. But we also know that this is equal to 2 to the negative 6, right? Because the reciprocal negates the exponent. So this is just 2 to the m times 2 to the negative 6. Okay, what about this side? This is 2, and then it's times the mth root of 1 over 4096. Well, 4096, like we've already talked about, is 2 to the negative 12, right? And we're putting that to the mth root. But the same thing as the mth root, the same thing as the mth root is the 1 over mth power. These are the same thing. So therefore, this is just 2 to the negative 12 to the power of 1 over m. Okay, so now we're getting somewhere because by exponent rules, this is 2 to the m minus 6, and using exponent rules over here, this is negative 12 over m. So this is 1 though, so we get 1 minus 12 over m. And then if we take the log base 2 of both sides, we just get this. And now this is just a quadratic we can solve. We just multiply both sides by m. Therefore, m can be either 3 or 4. And the sum of all the numbers m for which these two expressions have the same value is 3 plus 4 is 7. All right. Okay, this is AMC 10A problem 12, which is also 12A problem 9. On Halloween, 31 children walked into the principal's office asking for candy. They can be classified into 3 types. Some always lie, some always tell the truth, and some alternately lie and tell the truth. The alternators arbitrarily choose their first response, either a lie or the truth, but each subsequent statement has the opposite truth value from its predecessor. So basically, the first time they answer, it could be a truth, and then they would lie and then tell the truth, lie, tell the truth, or they could start with a lie and then lie, tell the truth, lie, tell the truth, lie, tell the truth, right? So that's what the alternators do. Okay, so the principal asked everyone the same 3 questions in this order. So we asked everyone, are you a truth teller? The principal gave a piece of candy to each of the 22 children who answered yes. Are you an alternator? The principal gave a piece of candy to each of the 15 children who answered yes. Are you a liar? The principal gave a piece of candy to each of the 9 children who answered yes. How many pieces of candy in all did the principal give to the children who always tell the truth? Okay, so this can be a lot to take in. This is the longest question on the exam by far. So it can be easy to get lost in all the words. But essentially what this is aside from a math problem, this isn't very much of a math problem. This is actually more of a logic puzzle. So we have to think about how we can categorize the children, right? We have to think about how we can categorize them so that we can express we can express 22 as a sum of like, oh, this group of children said yes. This group of children also said yes. This group of children also said yes. So I'll explain what the thinking is. Basically, we divide them into 4 groups. The children who are truth tellers, the ones that always tell the truth. The liars, who always tell the lie. I'm marking it with F here because F stands for false. So they're saying false statements. Okay. But yeah, the hard part about this problem is trying to figure out how we mark the alternators, because the alternators can choose to tell a lie or the truth at their first response. Well, let's just divide them into 2 groups. Alternators, who as their first response is a truth, and alternators who as their first response decide to lie. So basically, the truth-telling students will tell the truth, tell the truth, tell the truth, the lying students will tell a false statement, false statement, false statement. And alternating truth would tell truth and then false and then truth. And alternating false would tell false and then truth and then false. Okay, so now we are ready to set up the equations, right? Okay, so the first thing the principal asks is, are you a truth teller? And apparently 22 children answer yes. Okay, well, who would answer yes to that question? Well, the truth tellers would, because they're truth tellers, and truth tellers tell the truth. So they tell the truth that they always tell the truth, and they'd say yes. The liars would also tell the truth here. I mean, they wouldn't, they lie, right? And they're liars, which means they're not truth tellers, and they don't tell the truth. So they lie about being a liar. They'd instead say, yes, I am a truth teller, even though they're not, because they're liars. And then alternating truth is actually the only one who's going to say no, because they aren't truth tellers, but they're still going to tell the truth, right? So they're alternators, and they're on this phase, right? They're telling the truth here, right? Because they start by telling the truth. Those are ATs, right? And they're going to tell the truth that, no, I am not a truth teller. I'm an alternator. So those aren't going to be included in the sum. However, the alternating ones who start by with a false statement are also going to be included for the same reason as the ones who are always lying, right? They aren't truth tellers, and they're going to lie. So they're going to lie and say, yes, I am a truth teller. So that sum gives us 22 children who answered yes. Okay, let's go on to the next one. Are you an alternator? And apparently 15 children answered yes. Okay, who would answer yes to this question? Well, the truth tellers wouldn't, because they are going to tell the truth. They're going to be like, no, I'm not. I'm a truth teller. What about the people who lie? Well, the children who lie, they're going to say yes, because they aren't alternators and they want to lie. So they're going to lie by saying that they are alternators. The alternating ones that tell the truth, are they? Well, the thing is, actually, because they told a truth as their first statement, now they're telling a false as their second statement. Which means that now they're going to lie, and they're going to lie about being an alternator. They're going to say, no, I'm not an alternator. So they're not going to be included in the sum. And then finally, the alternators who are lying, well, those are going to be included because, as said before, they lied as their first statement, but now they're going to tell the truth. And since they are alternators and are telling the truth now, they're going to be like, yeah, I'm an alternator. So they're included. And now we could go on to the third one, are you a liar? And it would be the same process. And after that, we would get another equation. And then we could combine that with the fact that in total, all four of these groups equal 31 to solve for all four variables. But look at what the problem's asking. It's asking for how many pieces of candy the principal gave to the children who always tell the truth. But we already know that because we just subtract these two equations. You can just subtract them. And t is just 22 minus 15 is 7. Okay, this is AMC 10A problem 13. Let ABC be a scalene triangle. Point P lies on BC so that AP bisects angle BAC. The line through B perpendicular to AP intersects the line through A parallel to BC at point D. Suppose BP equals 2 and PC equals 3. What is AD? Okay, so let's try to draw this figure. I'm going to try to draw the figure as to scale as I can. There we go. So here is our triangle ABC. And the reason why I didn't draw it taking up the whole screen is because, as we're about to see, point D is going to be right around here. So if we draw the angle bisector of A, it's going to intersect here at P. And BP is 2, PC is 3. Well, now we're looking at the line through B perpendicular to AP. And we are intersecting that with the line through A parallel to BC. So let's draw some parallel marks. And the angle bisector, we draw that these two angles are equal, and this perpendicular. Okay, so this is a lot to take in for this problem. So the question is, where do we start? Okay, we need to clarify two things for this problem. The first is a theorem called the angle bisector theorem. The angle bisector theorem basically states that if we have the angle bisector in a triangle, right? And let's say we call this W, X, Y, and Z, then W over X is equal to Y over Z. In other words, these two ratios are equal if and only if this is an angle bisector. Okay. So how does this help here? Well, we can apply the angle bisector to this problem directly because we have an angle bisector and we have a ratio, which means that by the angle bisector theorem, this has to be 2 times some constant k, and this whole length here has to be 3 times some constant k. Okay, so now we're making progress because we have another ratio to work with, and actually we can make even more progress because AB, and now let's call this intersection point here, let's call it E. Oops, let's call this intersection point E. Well, we know that ABE is an isosceles triangle because these two angles are equal where there's a perpendicular, right? In other words, these two triangles are congruent. So we're putting two congruent triangles back to back, which gives us an isosceles triangle. And the reason why that's important is because we know that this length here is equal to 2k. And therefore, this length equals k in order to make the full length 3k. All right. And now we are at the end of the problem. And now there's one more thing that needs to be seen here in order to solve the problem, which is similar triangles, basically. In particular, this type of similar triangle is called bow tie. So what bow tie is basically if we have two parallel lines, two parallel segments, and we connect their endpoints in this fashion, these two triangles have to be similar to each other, which makes sense, right? Because these are alternate interior angles of the parallel lines, right? And these are also alternate interior angles. And bam, by AA similarity, these two triangles are similar. Okay, well, now, once I point this out, right, it might have not been so obvious at first, but now it's probably very obvious here that AEC and BED are similar in this sort of way. They're similar in this sort of bow tie fashion, right, with these parallel lines. And the reason why that's important is because they're parallel in a way such that the ratio of BC to AD is simply the ratio of CE to EA. But we know that the ratio of CE to EA is just 1/2. So therefore, AD is just 2 times BC. And since we know the value of BC is 5, then it's just 10 and we're done. Okay, this is AMC 10A, problem 14. It is also AMC 12A, problem 10. How many ways are there to split the integers 1 through 14 into 7 pairs so that in each pair, the greater number is at least 2 times the lesser number? So I'll just give some examples. For example, 4 and 9 works. 5 and 12 works. What doesn't work? Well, 3 and 5, for example. This doesn't work because, well, 5 is not at least 2 times 3, right? 5 is not at least 6. That is not true. So the question is, how do we approach this problem? Because if we just try to list out the solutions, we are going to run into a dead end very quickly. But the key thing here to notice is that while, for example, the number 1 can be paired with literally any number. It can be paired with any number from 2 to 14, right? Which isn't very helpful, right? So for example, we shouldn't start by pairing 1 to one of the numbers. That is not a good idea. What we should start with instead is the higher numbers. based in what I mean is the numbers 8 and higher. The numbers 8 and higher, 8, 9, all the way up to 14, because those numbers have to have numbers smaller than them, which really reduces the number of numbers, right? So let's try that. Let's start with 8. For example, 8, we can't have any of the numbers 9 through 14 pair with it because they're all greater than 8, but they're not at least 2 times 8 because 2 times 8 is 16, which is greater than 14. So it can only be paired with 1, 2, 3, and 4. And then if we go on to 9, we actually see the same thing happens, 1, 2, 3, and 4, because 5 is too big. 5 times 2 is 10, which is greater than 9. And if we list this out, we see that 10 can be paired with 1, 2, 3, 4, or 5. 11 can be paired with 1, 2, 3, 4, or 5. 12, I'll just write it over here. 12 can be paired with 1, 2, 3, 4, 5, or 6. 13 can be paired with 1, 2, 3, 4, 5, or 6. And 14 can be paired with 1, 2, 3, 4, 5, 6, 7. Okay, but why is this useful? Well, hopefully you can see that this is extremely useful. In fact, we can just solve the problem now because this shows us that 8, 9, 10, 11, 12, 13, and 14, they all have to pair with the numbers from 1 to 7. So we can just start by pairing 8 to one of the numbers, then pair 9 to one of the numbers, 10 to one of the numbers, and go up till we pair 14 to one of the numbers. And we can just count the number of ways to do that and we'll be done. And this is actually, if we start with 8, it gives us the easiest process and you'll immediately see why. For 8, how many ways are there to choose the number we pair it with? Well, 4, right? Obviously, we can choose 1, 2, 3, or 4. How many ways are there to do it with 9 after we choose 8? Well, there's 3 ways, right? Because let's say we choose 3. Well, no matter what number we choose, it's going to also be here, right? Because they pair with the exact same numbers. So once we pair with 3, for example, 3 will be gone from all of these, right? We can't pair 3 with any of the others. Okay, well, now let's say that with 9, we choose 1, right? That's the number we pick. Oops. Okay, well then we can't pick 1 for any of these numbers. How many ways are there to do 10 now? Well, there's 3, right? And there was no other way for it to not be 3, right? Because no matter what 2 numbers we pick for 8 and 9, those 2 numbers we pair them with is from 1 to 4. And 10 covers all the numbers from 1 to 5, which means that it'll cover those 2 numbers. And that's the really cool thing, right? 1, 2, 3, 4 is a subset of 1, 2, 3, 4 is a subset. And that's what finishes off this problem, basically, because all the numbers we choose from previous will affect the next one always, which allows us for a consistent way to count, right? So for example, for 10, let's say we pick 5, right? None of these numbers can have 5 anymore. Okay, what about 11? Well, now there's only 2 choices, 2 or 4. Let's say we pick 2. Okay, well, now we move on to 12. How many possibilities are there? Well, none of these and not this one, 4 or 6. There's only 2 possibilities. Let's say we pick 6. Okay, now 6 can't be done here, 6 can't be done here. Well, now 13 only has 1 possibility, and 14 only has 1 possibility. So this just gives us the product we need. 4 times 3 times 3 times 2 times 2 times 1 times 1. It follows this nice pattern that makes a lot of sense, actually, which is that each time we go down, well, every other 2, it goes down by 1, right? Which makes sense. And this is the product we need. 4 times 3 times 3 times 2 times 2 times 1 times. And this just product equals 144. Okay, this is problem 15 of the AMC 10A. Quadrilateral ABCD with side lengths AB equals 7, BC equals 24, CD equals 20, and DA equals 15 are inscribed in a circle. The area interior to the circle but exterior to the quadrilateral can be written in the form A pi minus B over C, where A, B, and C are positive integers such that A and C have no common prime factor. What is A plus B plus C? A, 260, B, 855. C 1235, D 1565, E 1997. Okay, so these are all very like the reason why I read them is because these are all very large numbers, right? Because we're going to get a fraction with very large numbers. This is actually going to be a pretty ugly solution, but anyways, this is going to be a quick problem if you know your Pythagorean triples. If it's not, then you're probably not going to be able to solve it because it's a lot harder without Pythagorean triples, or just, although the other way you could do it is, well, if you know what Pythagorean triples are, chances are you probably already know how to solve this. But if you don't know what they are, the other way you can see how to solve this is by drawing an accurate diagram. If you draw an accurate diagram in the test, right, you'll notice that ABC and ADC seem like right angles. They seem like right angles. And well, AC looks like a diameter of the circle. And if you look for a little bit and you realize that 724, that this is true, 7 squared plus 24 squared is 25 squared, and that 15 squared plus 20 squared equals 25 squared, then you will like realize that this diameter has to be 25. It has to be diameter and it has to be 25, and these are right angles. So basically, the entirety of this problem relies on finding the fact that AC is a diameter by figuring out that AB squared plus BC squared equals CD squared plus DA squared. That is actually a very common technique in problems like this, where they give you a quadrilateral inside a circle. Chances are one of the 2 points forms a diameter, and that can help you solve the problem. And now from here, it's not too difficult to solve because the area of the circle, well, that's just pi times 25 over 2 squared, right? Because our radius is 25 over 2. And then we have to subtract the area of the quadrilateral, which is 7 times 24 over 2 plus 15 times 20 over 2. And we can just put that all over 2. Right. So now we just get over here, 625 pi over 4 minus, and then over here we get 7 times 12, which is 84, and then minus 15 times 20 over 2, which is 150, which this just gives us minus 234. And now we just have to multiply 234 times 4 to get it onto the fraction. And this is why the problem gives you such large values, right? That makes sense why the answers are so large, because you have to add up very large numbers, basically. And if we multiply that out, we get 936, which means that our final answer is 625 pi minus 936 over 4. Yep. Yeah, okay, that's good, I think. And basically, at this point, we get our numbers A, B, and C. A and C have no common prime factor. That's good. Okay, and now we just find A plus B plus C, which is 625 plus 936 plus 4, which gives us the giant number 1,565, which is choice D. Okay. This is number 16 of the AMC 10A. The roots of the polynomial 10x cubed minus 39x squared plus 29x minus 6 are the height, length, and width of a rectangular box. A new rectangular box is formed by lengthening each edge of the original box by 2 units. What is the volume of the new box? Okay, well, this is related to something called Vietta's theorem, or Vietta's formulas, right? Vietta's, which basically this is just, you get it from the fact that, well, let's say that we know what the roots of this polynomial are, right? Let's say the roots are A, B, and C. Well, we know that the polynomial has to be x minus A times x minus B times x minus C in order to make all the roots make the function equal to 0. And then we know that this term is the x cubed term, and that has coefficient 10 in this problem. So we get this. 10 times x minus A times x minus B times x minus C. Well, what happens if we expand this? We get this. All right. And this is very helpful because, well, if we have the height, length, and width of a rectangular box to be these roots, A, B, and C, and then we add 2 to each side length, A plus 2, B plus 2, C plus 2, and then we multiply these together, that's what finding the volume is. We get ABC plus 2, AB plus BC plus CA plus 4 times A plus B plus C plus 8. And now we can just solve it because we know that this coefficient here, we know that this value is 39. Wait, no. Yeah, that value is 39. This value is 29, and this value is 6, which gives us that A plus B plus C is 39 over 10. AB plus BC plus CA is equal to 29 over 10. And this part gives us ABC is equal to 6 over 10, which basically means that our answer is just going to be A times B times C, 6 over 10, plus 2 times 29 over 10, plus 4 times 39 over 10, plus 8. And 8 is just 80 over 10, you could just say. Okay, and now if we just simplify this, well, this 2 times 29, that's just 58. 4 times 39, that's just 156. So we just get 6 plus 58 plus 156 plus 80 over 10. And if we add all these numbers up, we get, well, 64, 220, 300. Yeah, 300 over 10. All right, and that just gives us 30. That's our answer. All right, this is problem 17 of the AMC 10A. How many 3-digit positive integers A, B, C are there whose non-zero digits A, B, and C satisfy 0.ABC, ABC, ABC, ABC is equal to 1/3 of 0.AAAAA, right? Plus 0.PBBBBB plus 0.CCCCCC, right? Which happens as a result of this bar notation. Right? So this is 0.ABC, ABC, 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 0.AAA, right? So on forever. Okay. So there's something we quickly got to note here, which is the fact that this and this basically just 3-digit number ABC over 999. Okay, why is the first one true? Well, the first one is true because, well, let's think about it. If we take 0.A and we multiply it by 10, this gives us A point A, right? And if we subtract 0.A, this gives us 9 times 0.A, obviously, right? But this is also equal to just A, right? So basically, this is equal to A over 9, right? All right, so that makes sense. And now for the other part, for this second problem, right? I mean the second part, this part, which is the exact same steps, really. We have 0.ABC, ABC, ABC, ABC repeating, right? Well, what happens if we multiply it by 1000? Then we just get ABC dot ABC, 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 so on forever. And then we subtract 0.ABC repeating ABC, ABC, ABC. Well, this just gives us 999 times 0.ABC repeating, right? But at the same time, this also just gives us ABC. So this is just equal to ABC over 999. Okay, so glad that's cleared up. Now, And actually what I'm going to do here is, because ABC represents the 3-digit positive integer, it's a 3-digit positive integer, right? A, B, and C are digits. They're not being multiplied in this scenario, which is very confusing. So I'm just going to convert it into place value right now. 100A plus 10B plus C. And this is equal to 1/3 of A over 9, which is A over 27, plus B over 9 times 1 over 3, B over 27, plus C over 27. And now we can multiply all sides by 999, which gives us 100A plus 10B plus C is equal to 37A plus 37B plus 37C. And if we subtract 37A to this side, we get 63A. And then over here, this is supposed to be plus 27B and then 36C. And then these all happen to be divisible by 9. So we divide by 9 and get this. All right, and that's it. This is the equation that this is equivalent to. And now we can solve the problem using it. So the best way to tackle this is to take it one A value at a time. So for example, when A equals 1, there's only one solution, 1, 1, 1, right? When A equals 2, there's only one solution again, 2, 2, 2, right? And it might seem like for each value of A, the only solution is A, right? If we set them all to A, that gives us the correct sum, right? And we would think, oh, the answer must be 9 then. But that is not true, because there are certain cases where we can deviate from the solution A, A, A. And the way we do that is by either subtracting 4 from the value of B and adding 3 to the value of C, or we add 4 to the value of B and subtract 3 from the value of C. And the reason why that would give us another solution is because, well, we're just adding 12 and then subtracting 12, right? So in cases where we can do that, right, where it's a valid operation, where we can basically, because the reason why we can't do it with 1, 1, 1 or 2, 2, 2, for example, is because if we did it with 1, 1, 1, for example, if we tried to subtract 4, we would get -3, and here we would get 4, right? Which isn't, it's not valid, because A, B, and C all have to be positive integer digits, which means they have to range from 1 to 9. So the first time we can actually get a solution that's different from the singular solution, well, 3 through 3 isn't the first time, it's 4, 4, 4. And the reason for that is, well, we can add 4 to the solution for B, and we can subtract 3 from the solution for C. And we get 4, 8, 1, which is our first non-repeating solution. Okay, well, we can do the same thing with 5, 5, 5. In fact, we can do 2 different ways of doing it, which is we can subtract 4 and add 3, or we can add 4 and we can subtract 3. Both barely fit within the space of 1 to 9. This one just barely scrapes the bottom, and this barely scrapes the top. So this gives us 2 more solutions. And now, finally, 666 is the last one where we can do this. Basically, we subtract 4 from here, and we add 3 to here. And this is the last solution that is different from just repeating, because 777 is now too high, right? We have to at least add 3 or 4 to one of the numbers, but that'll give us 10 or higher, which is not a digit anymore. So we are just left with 777, 888, and 999. And if you count all the solutions, that's just 9 of the repeating. These are all the repeating solutions, plus these 4, which are the different solutions, right? The ones where they're not all equal. And that gives us our answer of 13. Okay. AMC 10A, problem 18. Let TK be the transformation of the coordinate plane that first rotates the plane k degrees counterclockwise around the origin and then reflects it across the y-axis. What is the least positive integer n such that performing the sequence of transformations t1, t2, t3, ... tn returns the point 1, 0 back to itself? Okay, so this can be a very strange problem to tackle because it's a bit hard to think about, right? So like, let me try to draw a diagram and we can try to get a feel for it. And then I'll show how you can make the problem like much easier to find a pattern with. So sometimes what you can do is when it tells you this, like as for example, it tells you a function that is a bunch of weird stuff. Chances are some of this stuff can be removed without changing really how the function works if you change some stuff around, right? So let's think about it. Let's start with 1, 0, right? Well, now we're going to rotate it 1 degree and then reflect it across the y-axis. That gives us, well, that's not, this isn't to scale, right? That's definitely not 1 degree. But there we go. That's kind of like, it gives us this point that is 1 degree away from this axis, right? And now the next part of the function we're going to do is we're going to rotate it 2 degrees counterclockwise, and then we're going to reflect it back. Okay, well, now it's 1 degree below the x-axis, right? And basically, what keeps happening is if we continue this, right, we rotate it 3 degrees. Now it's 2 degrees, and now we reflect it, right? Now it's 2 degrees above the x-axis, right? And of course, what we can do is we can simplify the problem by just getting rid of these rotations and instead just realize the fact that the pattern of the problem just goes, well, when we do T1, it ends up 1 degree above it, then it ends up 1 degree below it, then it ends up 2 degrees above it, then it'll end up 2 degrees below it, and then 3 degrees above it, and then 3 degrees below it, and it's going to continue like this, right? And the only time it can return back to itself is when it reaches 180 degrees or 0 degrees, right? Or 360, basically, right? Well, the first time it reaches 180, well, it's going to go like this. This is after T1, it ends up like here. And then after T2, it ends up here. T3, it ends up here. T4, it ends up here. T5, it ends up here. T6, it ends up here. And we're going to continue like this. And the first time we're going to reach the 180 degrees is all the way over here, which is, well, if we count odd numbers 180 times, we're going to end up at 359. But you might be thinking, well, we haven't reached 1, 0 yet. We're at -1, 0 now. But remember, this is us simplifying the function, right? We've gotten rid of the reflections. But if we include the reflections back, keep in mind that the way it's reflecting is that it reflects across the y-axis, and then it reflects across the y-axis again, and then it reflects across the y-axis again, like so. So basically, after it reaches this point, it will have reflected 359 times, which is an odd number of times. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 359, which brings it back to 1, 0. So hopefully that makes sense, and that explains why when we reach 359, it reaches the x-axis again, but it's at the opposite side if not for the reflections. But if we include the reflections, since there's an odd number of reflections, that is what returns it back to the origin. I mean, 1, 0. And that is why the answer is 359. Okay, now this is AMC 10A problem 19. Let Ln denote the least common multiple of the numbers from 1 to n, and let h be the unique positive integer such that 1/1 plus 1/2 plus 1/3 plus all the way up to 1/17 is equal to h over L17. What is the remainder when h is divided by 17? Okay. Well, first we should figure out how this ends up being h over L17, right? Well, let's try to get h in terms of itself, right? Well, L17, if we multiply by L17 on both sides, we get this. H is equal to L17 over 1 plus L17 over 2 plus L17 over 3 plus L17 over 4, all the way up to L17 over 17. But there's a key thing to note here, and that's the fact that, well, L17 is the least common multiple of the numbers from 1 to 17, which means that it's a multiple of 17, obviously, but 17 is prime. So from the numbers 1 to 16, we're not dividing the 17 out from L17, which means that all of these first 16 terms are multiples of 17, which means that it doesn't matter for what the problem is asking. The problem isn't asking for h. The problem is asking for the remainder when h is divided by 17. And, well, these terms are all integers that are 0 in mod 17, so we don't need them if we're looking for it in mod 17. And we just get this. This is what we're looking for. We're just looking for this in mod 17. Well, now we have to find L17. But the thing is, that's a much easier process than it sounds like, because L17, well, we just need to find the highest, like for example, for 2, let's just do the process and I'll show you how to find it the quickest way. Well, for 2, what is the factor, what is the power of 2 that needs to be in L17? Well, the answer is 4, because the highest power of 2 we can have that is less than or equal to 17 is 16, right? There is no point in having 2 to the 5, because the smallest number that would need to have 2 to the 5 is 32, which is way higher than 17, but 2 to the 4 is necessary. So 2 to the 4 is necessary and it is sufficient, which means 2 to the 4 is the first term in our prime factorization, right? And now we move on to the next prime number, which is 3. And the highest power of 3 is 9. That's the highest power of 3 that stays less than or equal to 17, which means 3 squared is a part of our product, right? And this all makes sense, right? Because we're looking for a prime factorization like this. And the reason for this is because if we find for each prime the highest power less than or equal to 17, then that means that there can't possibly be a number that doesn't divide L17, because that would mean that it would have more prime divisors in one of these prime divisors. But that would imply that it's larger than 17, because even just a prime power by itself would be greater than 17. So now, if we continue, 5 squared is too large for 17. 7 squared is larger than 17. 11 squared is larger than 17. 13 squared is larger than 17. And finally, we end up at 17. And this is what L17 equals. So we're done now, basically, because L17 over 17 is this whole product just without the 17, right? And now we just need to find that in mod 17. So this is our answer, this in mod 17. All right, so now you can just repeatedly multiply and take modulars until you get the answer. I'm just going to try to do it the fastest way possible, which is 7 times 11 times 13 equals 1001. This is 16, this is 9. 9 times 5 is 45, which is, well, 17 times 3 is 51. So this is actually -6, and this is -1. Which means that this whole product together gives us 6006. And if we divide 17 into 6006, we get remainder of 5, and that's our answer. Right. Now, this is AMC 10A problem 20. A 4-term sequence is formed by adding each term of a 4-term arithmetic sequence of positive integers to the corresponding term of a 4-term geometric sequence of positive integers. The first 3 terms of the resulting 4-term sequence are 57, 60, and 91. What is the 4th term of this sequence? A 190, B 194, C 198, D 202, D 206. Okay. Well, let's try to define this sequence, these sequences. Well, for the geometric sequence, it goes A and then AR and then AR squared. Right? And then the next term would be AR cubed, but we don't need to write that. And then for our arithmetic sequence, let's just write B and then B plus D and then B plus 2D, right? So this all makes sense because geometric sequence, we're multiplying by the same consistent ratio, right? AR squared. Arithmetic sequence, we're adding the same difference D. B plus D, B plus 2D. So the key thing to notice in this problem is that it is, even though we could try to just set everything equal and try to solve for them, what's actually like key to notice is that we have 4 variables and 3 numbers given that define them, which means we only have 3 equations to define these 4 variables. So this isn't actually a solved equation right off the bat. This is actually just it's a Diophantine equation, which means it's working in the integers, and it's working in the integers, in the positive integers, that gives it a solution, right? So we have to get clever. We can't just like force solve it because we only have 3 equations for these 4 variables. So the clever thing to notice here is that the common difference is AR minus A plus B plus D minus B, which is just D, is 3. And AR squared minus AR plus D, like, because this difference is also D, is, well, 31. And now we can do something really clever, and we can subtract this equation from this equation and get AR squared minus 2AR plus A is equal to 28. And this is very clever because this can be factors as A times R minus 1 squared is equal to 28. And this already gives us very few solutions, right? Because, well, A is restricted to the positive integers because A has to be a positive integer because A itself is a term, and R has to be a positive integer because if R was not an integer, if R was not a, well, technically R doesn't actually have to be an integer, but because A is an integer and 28 over A is an integer, that means that over here, R minus 1, basically R would have to be an integer, because if it's not, then it would not make sense. Basically, anyways, the point is that we can try different integers A that divide 28. And the only ones that can work are if A equals, well, 28, and then R minus 1 is equal to 1, right? Which makes R equal to 2. Or A is equal to 7 and R minus 1 is equal to 2. Which makes R equal to 3. And these are the only 2 solutions. And if we try the first one, A equals 28 and R equals 2, we'll see that it doesn't work. And the reason why it doesn't work is because, well, these numbers, right? The arithmetic sequence actually works just fine. Everything works perfectly, except for the fact that negative 21 is not a positive integer. It's a negative integer, which contradicts with the fact that they're all supposed to be positive integers. Other than that, everything works, right? All the sums work and they're arithmetic and geometric sequence, but it just doesn't work like that. So this solution can't work. But if we try this one, we get an answer, which is 7, 21, 63. And then over here, the arithmetic sequence is 50, 39, 28. And this is what we needed, right? Because these sequences are all positive integers. And now we can just solve for the 4th term of the sequence. 7, 21, 63 becomes 189 on the next term. And 50, 39, 28 becomes 17 on this next term. And summing the 2 of these numbers up gives us 206. All right. So this has been the AMC 10A problems 1 through 20. And if you want more practice with problems of these difficulty, you can get these MathTopia books on Amazon to improve your problem solving skills.